to seminars or seminar of nonlinear system. You hear me?
Yes.
Okay, thank you. And today we will start with backstepping, and we make some examples, some easy example, and then we calculate some example with robust, yeah, some robust backstepping example. Okay, and let's start the whiteboard. Okay, first example is very easy. And it's like x, sorry. x1 dot equal to x1 squared plus x2 and x2 dot equal to u. The input, this one, take like input and stabilize the first row. Okay. Let's write first row x1 dot equal to x1 squared plus some additional input u with wave, and now we need to choose some control to stabilize this row. Any idea? x1 dot. Okay. U is wave equal to what we need to do. We need to cancel this nonlinear term x1 squared and put some control to this first row, then the final system x1 dot equal to x1 squared plus, and this x, sorry, here minus, yeah, minus x1 squared minus x1, and it's equal to minus x1. Yeah, and first we stabilize first row. We can check it with somewhat null function v from x equal to 1/2 x 1 squared. Sorry, this only v from x. And
I'm sorry, I'm not sure if I'm the only one, but I can't see what you are drawing. I cannot. Yeah, I have the same problem.
You have some problem with this whiteboard. I need to reconnect or something like this.
Maybe. I don't know where's the issue, but if we are connected, we don't see your updates on the whiteboard. Only when we disconnect and reconnect to the call, we can see what has changed. So I'm not sure.
I try to stop
maybe
whiteboard, and I try to reopen. Yeah. Okay, maybe now it will be okay. Okay, do you have any question in this step? Okay, and I hope now you see this whiteboard. and we
yes, now okay, thank you.
Yeah, now it's okay. Okay, v dot from x equal to 1, sorry, not 1/2, but now it's x1 dot is equal to x1, and this x1 dot, we take this part, okay, this x1 dot, put here, okay, and x1 and x1 squared minus x1 squared minus x1 is equal to minus x1 squared. Okay, we check that this system is global asymptotical stable. Yeah, this first row, but we know that it's stable. It's less than 0 for all x1 not equal to 0. Okay, and now the next step is we need to define the next variable z2, which include virtual control U with wave. Yeah, this z2 equal to x2 minus, this is difference between original x2 in first row and this virtual control U with wave. Yeah, and then okay, and then x2 equal to z2 plus U with wave, and z2 equal to x2 minus, and put this U with wave, this minus x1 squared minus x1, this equal to x2 plus x1 squared plus x1. And now we have the original system in new form, and this first first equation in original equation change form to the another with adding parameter. Okay, and now we only rewrite in new variable this x1 dot equal to x1 squared plus x2. Okay, we know, and now we rewrite it. It's equal to x1 squared and plus, and now we put here we put this part, not in x2 but now z, and this is, and plus z2 plus U with wave. Yeah, it's equal to x1 squared plus, okay, plus z2 and plus this U with wave, and U with wave is minus x1 squared minus x1. Okay, and this all equal to any step. Okay, and this equal to equal to minus x1 plus z2. Yeah? And z2 dot equal to, and x2 dot, because now we need to derivate this, this part. And we derivate this part, this x2 plus x1 squared plus x1, and the derivation is x2 dot plus 2x1 x1 dot and plus x1 dot. Yeah. And this is x2 dot, okay, and it's equal to u, because we know that x2 dot equal to u in our original equation. Yeah, and we put this u, and then plus x1 dot here, 2x1 plus 1, and it's equal to u plus, and this x1 dot equal to this this equal to this, yeah, and x1 u plus and this minus x1 plus z2 and 2x1 plus 1. Yeah, and now we need to design the Laplace function, or our control via the control Laplace function, and let's v from x equal to 1/2 x1 squared plus 1/2 z2 squared. Okay, and v dot from x equal to x1 dot plus z2 dot, it's equal x1, and here our x1 dot equal to minus x1 plus z2 and plus z2, and z2 equal to u plus minus x1 plus z2 times 2x1 plus 1. Okay, and now we need to design something, some control U, and okay, and what we need to do, we need to cancel all this term here, yeah, this term, and put some z2 with minus, yeah, and okay, and u equal to minus z2 and minus x1 plus z2 2x1 plus 1. Yeah. And z2, sorry, I know. And minus here it's Okay, here is some minus x1 here. Yeah, I forgot about this, but this term. Yeah, sorry, not this term, but this term. Sorry, this term. Yeah, and we need to cancel this term too. Yeah, and minus z2 minus this part and minus x1. Minus x1. Yeah. And then if we put this control, we dot from x equal to minus x1 squared and minus z2 squared. And system is globally asymptotically stable. Yeah. And for implementation this control to our original system, we need to change this z2, yeah, rewrite like this z2 equal to x2 this, yeah, x2 plus x1 squared plus x1 in original coordinate. Yeah. Okay, and u equal to and this minus, and this z2 is x2 plus x1 squared plus x1 minus x1 and minus x1 plus x2 x1 squared plus x1, this term cancel, and two x1 plus 1. Okay, and this all equal to, okay, this all equal to minus x2 minus x1 squared minus x1 and minus this x2 plus x1 squared and times 2x1 plus 1. Yeah. And this all put together. This is minus 2x1, yeah, and so on. Any question? Okay. Okay. And okay, now we try another solve another example. It's very similar. x1 equal to x1 squared plus, sorry, not plus, but plus x2 and minus x1 cubed and x2 dot equal to u. Okay, and what we need to do, first step, do you have some idea?
We need to replace in the first equation the x2 with virtual control u hat and stabilize the first system or first equation.
Okay, u hat u wave equal to, and what we need to do? Any idea? Can someone design this U with wave?
Well, can we, for example, say that U hat is equal to x1 minus x1 squared plus x1 to the third power minus x1 to make it into linear equation?
Sorry, minus and minus. Okay, minus x1. Okay, and in this step we can choose maybe another U wave equal to any another idea. Okay, x1 squared minus x1. Yeah, for example. Something like this, because this term is a good term and we don't need cancel this term, or we can cancel this term, yeah, and or we can use this universal Sontag formula and then put something, yeah. But okay, this first we'll start with this first, and it's very similar. This first U with wave, put it to first row, and x1 dot equal to x1 cubed squared minus x1 cubed and plus this U with wave, it's equal to x1 squared minus x1 cubed plus x1 cubed minus x1 squared and minus x1, yeah. This was all equal to minus x1, yeah. Okay, and you can do the same steps like in this example before, yeah, because I think it will be very same, yeah. For example, here it's minus x1, okay, and we know that this U with wave stabilize, yeah, and so on. Or for example, we can choose this second, yeah, and when we choose this second, it's like x1 dot equal to x1 as squared minus x1 cubed and minus x1 squared minus x1, so equal to minus x1 cubed, yeah, and it's practically the same like previous U with wave. And okay, let's take positive Laplace function v from x equal to 1/2 x1 squared, and the derivation is equal to x1 dot equal to x1, and this minus x1 cubed is equal to minus x1 squared minus x1 in 4th degree, and for all x1 not equal to 0, it's negative definite, yeah, and asymptotical stable. And then we make the next step is z2 equal to the same x2 minus this virtual control U with wave, yeah, and from this we have x2 is equal to z2 plus U with wave, yeah, and z2 equal to x2 minus, and this virtual control is minus x1 squared minus x1, and it's equal to x2 plus x1 squared and plus x1. Yeah, and now the same, rewrite this first row in a new coordinate x1 and z2. x1 dot equal to x1 squared minus x1 cubed and plus x2, it's equal to x1 squared minus x1 cubed and plus, and now we need to put this x2, and this x2, this is this part, yeah, this plus z2 plus u with wave, yeah, and this is equal to x1 squared minus x1 cubed plus z2 and plus this virtual control u. This virtual control u, I know that this is minus x1 cubed minus x1. Yeah. And okay, and it's equal to minus x1 cubed and plus z2. Yeah. Okay, and z2 dot equal to, and we know that z2 equal to this. Yeah. This is x2 dot plus 2x1 dot and plus x1 dot. This will equal to okay, x2 dot equal to u, yeah, u plus 2x1, and this x1 dot, this part, yeah, we go this, yeah, and this x1 dot, it's minus x1 cubed plus z2, yeah, cubed. Okay, and plus x1 dot and plus the same minus x1 cubed and plus z2. Yeah. Okay, and what we need to do now? Okay, we can make expression, simplify. It's equal to u and plus 2x1 and plus 1. Yeah, and this minus x1 cubed and plus z2. Yeah. And now we take a positive definite function v from x equal to 1/2 x squared plus 1/2 z2 squared, yeah, and the derivative equal to x1 dot plus z2 dot. It's equal to x1. Now this x1 dot minus x1 cubed and plus z2, and the second part, okay, and plus z2 times this u plus 2x1 plus 1 and minus x1 cubed and plus z2. Okay. Okay, and now we need to cancel. Okay, and now we need to design U. Okay, do you have some idea what we need to do?
Well, we can cancel the second term in the Z1 part. So U is equal to negative those two, 2 times x1 plus 1 times negative x1 to the third power plus z2. And then we also need to cancel the term x1 plus z2, or x1 times z2, sorry, from the first part.
x1, yeah?
Yeah.
Yeah, because you see that this is x1 times z2, and now it's z2, yeah, and we need to cancel this minus x1, yeah? Okay, and we need to put some, and the last term is
Negative z2, z2, sorry. To
okay.
have, okay.
Okay, thank you. Yes, right. When I put this control to our derivative of Lyapunov function, then v from x equal to minus x1, yeah, and from this part, yeah, from this part is minus x1 squared minus x1 in 4 degree, and we cancel all this. We cancel this term, yeah, and minus z2 squared, yeah, and okay, and now we need to, and we know that for all x1 z2 not equal to 0, v dot is negative definite, yeah, and system is global asymptotical stable, and we need to rewrite this u in our original coordinates. U equal to, here is minus 2x1 plus 1, it's okay, and minus x1 cubed and plus, and we need to put this z2, and z2 is equal to x2 plus x1 squared and plus x1, yes, and okay. Okay, and minus x1 and minus z2, yeah, and we know that z2 is x2 plus x1 squared plus x1, yeah. Okay, and here, for example, we cancel this term, yeah, this term, yeah. Okay, Any question? Okay, let's solve another example. X, okay, example 3, x1 dot equal to x1 squared. It's the same like our last example. Yeah, the first row is the same, minus x1 cubed and plus x2, and this x2 dot equal to x3 and x3 dot equal to u. Yeah, and the system consists of our previous example, yeah, the system in previous example, and additional integrator on input, and we can make a same procedure like in previous example, yeah, and after the first step we have the second order system. This x1 dot equal to x1 squared minus x1 cubed and plus x2, and x2 dot equal to x3, and x3 is a control law. Here x3, this x3 equal to, we know from previous example, yes, that u equal to this minus x2, okay, and we know that x3 is equal to minus x2 minus x1 squared and minus 2x1 minus this minus x1 cubed plus x2 plus x1 squared and 2x1 plus 1. Yeah, because this is the same. This is this u. Yeah. Now we're using this u in this next example. We know if we need, we can stabilize this all these two rows with this x3. Yeah, x3 like this virtual input. Okay, and we only say that this all is some defined like phi from x1 x2. Yeah, and function v from x v from x1 and x2 equal to 1/2 x1 squared plus 1/2, and here we need to put this z2 from previous example, yeah, this x2 plus x1 squared plus x1, yeah. This is appropriate upon function, and the step 2 is we need to stabilize the third row, yeah, and these 3 equal to x3 minus this phi from x1, x2. Yeah. Okay, and then x3 equal to z3 plus this function from x1, x2. Okay, and therefore x1 dot equal to x1 squared minus x1 cubed and plus x2 dot equal to z3 plus this phi x1 x2, this function, yeah, and z3 dot is equal to u minus this phi the x1 and this x1 squared plus minus x1 cubed and plus x2 and minus partial derivation x x2 and this 3 plus this phi from x1, this function from x1, x2. Okay, and we need to use the composite Lyapunov function equal to v plus 1/2 z3 squared, and then we can calculate the derivation v from c of composite function and so on. I put this example to Moodle, yeah, the complete solution, and because we know we don't have many time and we need to solve examples with robust backstepping, and I stop here with this example and I put the complete solution to Moodle. Yeah, maybe this example from Khalil book, I don't know. Yeah, and you can check the final solution in this book. Yeah, and now I solve another backstepping example. This x1 dot equal to minus x1 and plus x1 squared x2, and okay, and this x2 dot equal to u, and we need to stabilize this first row. x1 dot equal to minus x1 plus x1 squared and times u with wave. Any idea what we which control we can choose for stabilizing this first row?
Well, maybe, oh no, that's not very good control, but 1 over x negative minus 1 over x1, but that would not work for x1 at 0. So
maybe some easy solution.
Okay, just negative 1 or negative x1 to have.
Okay, We can choose negative x1. Okay, thank you. And some more idea. Another idea. Okay, thank you. Yeah. It's very simple. We can choose 0. Yeah. Or we can choose this minus x1. Yeah. It's okay. We can do it. Yeah. Choose this minus x1. Yeah. Both is right. Yeah. Both solutions are right. But we choose this first. Yeah. It's more easy. Yeah. And our particle is the same. But when we put it to x1 dot to the first row is equal to minus x1 plus x1 at 0 is equal to minus x1. Yeah. Okay, and we only check v from x equal to 1/2. Only check if our solution is correct, and v from x, v dot from x equal to x1 is x1 dot, and it's equal to x1 minus x1 is equal to minus x1 squared. It's less than 0 for all x1 not equal to 0. Negative definite, and the system is global asymptotical stable. And now we make next step, step 2. We need to define the variable z2. Okay, z2 equal to x2, yeah, and minus this virtual control with wave, and for this we know that x2 equal to z2 plus u with wave, yeah, and you see that z2 equal to x2 minus 0, it's equal to x2, yeah, it's perfect, yeah, because z2 equal to x2, it's very easy, and what we need to do now, we need to rewrite the first our system in new variables, in new coordinate. x1 dot equal to minus x1, this plus x1 squared x2, it's equal to minus x1 plus x1 squared and times x2, and x2 equal to the same step, yeah, put here this z2 plus u is wave, yeah, and okay, and it's equal to minus x1 plus x1 squared and only z2, yeah, because this u equal to 0, yeah. Okay, and the next row z2 dot equal to x2 dot, and x2 because z2 dot equal to x2 dot and equal to u, yeah. And now we need to design this v from x 1 z2 equal to 1/2 x1 squared plus 1/2 z2 squared, yeah, and the derivation v dot equal to x1 dot plus z2 dot Okay, and it's equal to x1, and here this minus x1 plus x1 squared z2 and plus z2 and z2 dot is u. Yeah, yeah, only u. Yeah, and it's equal to what? Minus x1 squared plus z2. Here it's x1 cubed and plus u. Yeah, something like this. Yeah, and now we need to design u to stabilize this system. Okay, can someone design this u?
For example, negative x1 to the third power minus z2.
Okay, thank you. Yeah, exactly. Yeah, and when we put this u, then v with dot equal to minus x1 squared minus z2 squared. Yeah, and we put this control here. Yeah. Okay, and now for implementation we need to change this z2, yeah, and u equal to what? Minus x1 cubed minus what? Z2 equal to what? Z2 equal to
x2.
yes, x2. Okay, and yeah, x2. Okay, and now we can use this control and put it to our system, and finally we can stabilize the original system with this type of control. Yeah. Any question? Okay. Okay, let's do another example. I don't know, maybe.
Can we, for example, do some example for backstepping?
Yeah. Now I want to.
Okay, thank you.
Okay, I put more example with solution to Moodle today. Yeah, and you can read and maybe prepare to our test, and now we make some example with robot backstepping. Okay, and okay, and first example is x1 dot equal to x2 plus x1 times cosinus r x2 divide 2 and x2 dot equal to u. Yeah, and here this yeah. Okay, and now we need to design u, yeah, without precise knowledge of parameter r. Yeah. And okay, we will use the next inequality, cosinus rx2, yeah, always less or equal to 1. Yeah? And from this, x1 cosinus rx2 divide 2, the absolute value is less or equal to x1 divide 2. Yeah? Any question here? Okay. And now.
Yes, why are we using absolute values here? Are they necessary?
Yes, it's necessary because when we.
Oh yeah, I see it already. So, sorry.
Yeah, because when we calculate the derivative of Lyapunov function, then we need to choose some worst case, yeah, and worst case is when it's a maximal, so some positive number, yeah, because when it's negative, it's okay and it's good, but when it's positive, it's bad, yeah.
Okay, thank you.
Okay, and now we start with first step. Yeah, first step is we need to choose some virtual control. Yeah, and okay, we say that x2 is equal to take this x2 like a virtual input. Yeah, and it's not equal. Maybe it's not good. Then I only write this first x1, first row x1 dot equal to x1 cosinus rx2 divide 2 and plus virtual control U with wave. Yeah, and
sorry, can we write it like this, because we now have both virtual control and the variable x2 in the same equation?
We can, yeah, we can, because we say okay, but cosinus r from x2 is less than 1 or equal to 1. Yeah, and now we take only this x2. Yeah, and we can do it. Yeah. Okay, and now we need to design control U. It's equal to sum minus Q1 x1. Yeah, and when Q1 is less than 0, some positive number, some positive, and x1 dot equal to minus Q1 x1 and plus this x1 cosinus rx2 divide 2. Yes. Okay, and now we from x1 equal to 1/2 x1 squared and and the derivative of x1 of v from x1 equal to x1 dot times x1 dot and it's equal to x1. Here's this minus Q1 x1 plus this term with cosinus, yeah, and plus x1 cosinus rx2 divide 2. Okay, and it's less or equal to x1, here minus Q1 x1 and plus, and here only x1 divide 2, yeah? And it's equal to minus Q1 minus 1/2 x1 cubed. Yeah. Any question in this step? Because we say that this inequality, yeah, we use this inequality, and then, and now you can see that why we this x2 is it's no matter, yeah. You can because this all is less or equal to x1 divided 2, yeah, and here is for all x1 not equal to 0, we dot from x1 less than 0 if k1 greater than 1/2, yeah. If k1 greater than 1/2, then our system is global asymptotical stable, yeah, and v dot is negative, yeah, definite. And now we need to make step 2. Okay, step 2 is z2. Define next variable z2 equal to x2 minus u with wave, yeah, and x2 equal to z2 plus u with wave, and put this control u with wave, and z2 equal to x2 minus q1 x1, yeah, and it's equal to x2 plus q1 x1, yeah. Okay, and now we need to rewrite our system in new variables. X1 dot equal to x2 plus x2 plus x1 cosinus rx2 divide 2 is equal to z2 minus q1 x1, yeah, because z2 equal to x2 equal to z2 minus q1 x1, yeah, and z2 minus q1 x1 and plus this x1 cosinus rx2 divide, and now, sorry, now we need to use this z2, yeah, it's plus x1 cosinus sorry, cosinus r times, and this x2 equal to z2 minus q1 x1, yeah, and this divide 2, and z2 dot equal to, we know that z2 equal to x2 plus k1 x1. Okay, this is x2 dot plus k1 x1 dot. Okay, and it's equal to x2 dot equal to u and plus k1, and we need to and x1 dot. This is z2 minus k1 x1 and plus, plus this term x1 cosinus r and z2 minus k1 x1 divide 2 and okay, something like this. And now we design the control the Lyapunov function, this v from x v from x1 z2 equal to 1/2 x1 squared plus 1/2 z2 squared, yeah, and v dot equal to x1 dot plus z2 dot, it's equal to, and now we need to rewrite all this terms. It's equal to x1 and this x1 dot equal to z2 minus k1 x1 plus this big term with cosinus x1 cosinus this r z2 minus k1 x1 divide 2, okay, and plus z2 times z2 dot, this u plus k1 and z2 minus k1 x1 plus this term with cosinus x1 cosinus r times z2 minus x1 minus k1 x1 all divide 2, so 1 and 1 more, yeah, yes, and okay, yeah, and in this step we can say that this all is less or equal to, and this x1, this z2 minus k1 x1 and plus x1 divide 2 and plus z2 times u plus k1 x1 and okay, 1x1, but sorry, 1, and this z2 minus k1 x1 and plus x1 divide 2 plus x1 divide 2 and okay, and this all is less or equal to minus k1 minus 1/2 x1 squared and plus z2 and x1 plus u plus u plus k1 z2 my plus z k1 z2 minus k1 x1 and plus x1 half. Okay, and now we need to design our control U. Okay, and says that control U is equal to minus x1 because we need to cancel this term, this bad term x1, yeah, minus x1 and minus k2 z2. Okay, because when we put it, okay, only this term k2 z2, yeah, and now we need to put this u in our last equation, this v dot from x1 x2 z2, sorry, z2 less or equal. You hear me?
Yes.
Yeah, thank you, because because my PC is very slow, and this whiteboard. Okay, and when we put, then the final minus k1 minus 1/2 x1 cubed, yeah, this first part, and plus this z2, and now we put this u here, and we cancel this first minus this first x1, yeah, and we stay with k1 minus k2 z2, and this term plus k1 z2 minus k1 x1, sorry, minus k1 x1 and plus x1 divide 2. Okay, and okay, one more, and it's equal to this also, and it's is equal to minus k1 minus 1/2 x1 squared plus okay, what we can see is that plus open and k1 minus k2, okay, z2, oops, because here, yeah, this term k1 with z, and here this term, yeah. Okay, and the last term is minus k1. It's come from this part. This minus k1 squared. Yeah. This is this part. Yeah. And this is z2. And k1 squared x1 z2, and the last term in plus here k1 and z2 at k1 z2 x1, and so divide 2, yeah, something like this, yeah. And now we need to find the appropriate condition of k1 and k2 for which our the derivative of Lyapunov function is negative definite, yeah. This is the last step. And okay, and we dot from x1 z2 equal to x1 z2, and all right, matrix. And this first term with x1 squared, yeah, this is minus here. It's 1/2 minus k1. Yeah. This term comes from this part, yeah. Okay, and the next term is with z this one, yeah, with z2 squared. This term is k1 minus k2, yeah. Okay, and we need these two terms, yeah, this k and this term, this and this, yeah, and this minus okay, and this term is minus q1, sorry, this term is q1 1/2 minus k1, so divide this, all divide 2, because we need split this term between these two, and the same term here, K1 1/2 minus K1 divide 2. Okay, and this all this vector x1 z2. And now we need to check the condition when this quadratic form is negative definite. Yeah, it's Sylvester law criterion. I think you may remember. We saw some example on first or second seminar. Yeah, and we know that the quadratic form is negative definite if d1 is less than 0 and d2 greater than 0. Yeah, and okay, d1 in our case, this term d1 equal to 1/2 minus K1 is less than 0 and 1/2 and K1 is greater than 1/2. Yeah, but we know this condition from our first step, I think. Yeah, when we say that K1 is greater than 1/2. Yeah, and the second is d2. We need to calculate d2 is equal to 1/2 minus K1 times this term K1 minus K2 and minus this term K1 divide 2 and times 1/2 times 1/2 minus K1. K1 minus, and this all, yeah, squared. This all we need greater than 0. And okay, and when we make some calculation, yeah, you can find that K2 is greater than K1 squared 1/2, some estimation, yeah, 1/2 K squared divide minus 1 and plus 1. Yeah, and what you need to do, okay, but the last step, we need to do some last step, and the last step is this U equal to, and we know that U equal to minus x1 minus K2 z2, and it's equal to minus x1 minus K2 and this z2 is x2 plus K1 x1. Yeah, sorry. it's equal to minus 1 plus k2 k1 x1 minus k2 x2. Okay, and when we choose, we need to choose some k1. For example, I don't know, k1 equal to some idea, for example, maybe
1.
Okay, 1, yes, 1. Okay, k1 equal to 1, and k2 equal to what we need? K2 equal to what? It's 1, 1/2, 1, 1. Okay, and you can put this 1 here and calculate it, and then say, okay, k2 equal to something, yeah? And that's all. Any question? Okay, and we guarantee the global exponential stability of the system because the Laplace function is quadratic and its derivative along trajectory is negative definite, yeah, quadratic form. Someone use this condition in the last homework, yeah, and only say that v dot is less than minus alpha v. Yeah. Okay. Do you have any question?
Can I ask about the test that we are going to take the next week?
Yes, I give you some tests. I put it to Moodle, and maybe it will be start. It will be open in the right time, like our seminar. But maybe I give you 5 or 10 minutes more. Yeah, for example.
And the form is that we are going to get some questions. I'm not sure about the form.
You receive three tasks and need to calculate, and I think you receive some form or something like this. I prepare a test this week, and I write you a mail, yeah, with some data information about test. Yeah.
Okay, thank you.
And now, if you want, I can only start with the last example with Robux backstepping. Yeah. I only show you first step, only first step, yeah. It's x1 dot equal to x2, x1 dot equal to x2, and x2 dot equal to some alpha sinus x2 plus u, yeah, and alpha from some minus alpha max and plus alpha max. Yeah, and alpha max real, yeah, and alpha max greater than 0, yeah. Okay, and I want to show you only this inequality, only some estimation, first step, that when we have this sinus, we can estimate it's like this. We know the sinus from x2, the absolute value is less or equal to x2, absolute value, yeah. And then alpha sinus x2 less or equal to alpha max, because the absolute value is maximal value is alpha max and x2. Yeah, and then we can do something like in previous example, yeah, and introduce new state coordinates, and I put this example with solution to Moodle today, yeah, and you can recalculate at home, yeah. Okay, and do you have any question? Okay, thank you, and see you next week. And if you have any question, you can write me a mail, yeah, and I put homework with backstepping to Moodle, yeah, and you can do it. And if you have some question, you can ask me, yeah. And thank you. Goodbye.
Bye.
Goodbye.
Bye.